In this video, I will show you how to find the magnitude of the magnetic field from a single charge. In my previous video, I showed you how to find the vector, the XYZ components of the magnetic field. In this video, I will focus on calculating just the magnitude. This number, of course, will not show me the direction of the magnetic field. This number will simply show me the strength of the magnetic field at the observation location. This here is Biot-Savart's law for a single moving charge, and as I said before, what I want to find now is just the magnitude. And because the constant mu naught over 4 pi is a positive number, I don't need to place it in absolute value. But the source charge can be positive or negative, so I will place it in an absolute value. And then I need to use the magnitude of the cross product. And the magnitude of the vector r is always a positive number, so I don't need to worry about that. Now, everything else is clear but the magnitude of the cross product. I can make this a little bit more simple by saying I know that the magnitude of a cross product is equal to the magnitude of the first vector times the magnitude of the second vector times the absolute value of the sine of the angle theta. And then I need to divide this as usual with the magnitude of r squared. Now, there is something that makes my life easier. Yes, there is. The magnitude of r hat. R hat is the unit vector, and it has the property that it has a magnitude of 1 always. So I don't have to do this calculation. I know it is 1. So I have the constant, the absolute value of the source charge times its speed times the absolute value of the sine theta divided by the magnitude of r squared. Now let me show you an example. Let's say that the charge 1 is an electron. So Q1, my source charge, will be minus 1.6 times 10 to minus 19 coulomb. It is moving to the right, but it doesn't matter. What I'm looking for, what I need is the magnitude. Let's make it move with the speed of 12 meters per second. And let's say, since this is where the observation location is, okay, let me show you the vectors. So this will be R2. This here will be R1. The vector that goes from 1 to 2 will be this one. So this is the vector that goes from 1 to 2. Now, take a look here. This is because the observation location is on the same x value. The angle between the two vectors v and r, or r hat, they point in the same direction anyway. This angle is 90, and the sine, I know that the sine of 90 is 1, so theta is 90 degrees, which means the sine of theta is 1. What else do I need? I need the magnitude, and let's say that the distance between those two let's make that to be 2 meters. Now, in this example, I'm giving you what the distance is. It is possible in a problem that you will be given the position of the source charge, the position of the observation location, like the two vectors, and you will be asked to find the magnitude of the magnetic field. In that case, simply do follow the steps as usual. Find the vector r, find the magnitude, and that will tell you what the distance is. In this case, I'm giving you this number. So for the calculations, I have the constant 10 to minus 7, the absolute value of the charge Q1, and I don't have to worry about the minus sign since I'm using the absolute value. The speed times the sine of theta, which is 1, and I have to divide this with 2 squared. Now, the way that I like to do these calculations is to separate the powers of 10 with everything else. So 1.6 times 12 divided by 4 times 10 to minus 26. And then this will give me simply 3 times 1.6. Tesla. This is the magnitude of the magnetic field at the observation location. This is a much more simple calculation. Finding the magnitude of the magnetic field is much more simple than finding the vector. I do want to mention something that is relevant, but is not directly related with what I've done so far. That was an example of how to find the strength of the magnetic field. Now, I want to spend a few minutes explaining or find when does the magnitude of the magnetic field become 0. Okay, I know that the magnitude of any vector has to be either a positive number or 0. Now, what I want to find is when does this become 0? If I take a look at my result for the strength of the magnetic field, I have a constant. I don't control that. Q1, I don't control that. So long as you have a charge, this is not 0. And this is the distance between your observation location and the source charge. And this cannot help me make unless you go really far away. We're not looking into that. I want to find at what observation locations around the charge, near the charge, the magnetic field will be 0. So the speed, if the speed of the particle is 0, which means if my charge is not moving, then this will tell me that the magnetic field is 0. So let's make a note. If the speed of the source charge is 0, then this means that the magnetic field that this creates around it is 0. This is important. If your charges are not moving, they do not create a magnetic field around them. None. Nowhere. If the charges are stationary, the only thing that they do is create electric fields around them, but no magnetic fields anywhere around them. Now, okay, if I make the assumption that they are moving, their speeds are not 0, then the other possibility will be to get a 0 from making the sine of theta equal 0. If the sine of theta is 0, then the magnitude of the magnitude of the magnetic field is also 0. But the thing is, when does this become 0? Remember, the angle theta is the angle between the velocity vector and the r vector. So this means if your charge is here, if this is your source charge and it's moving this way, this is V1, the angle theta will be 0 when the observation location is here. So that the vector r will point in the same direction as V1. In this case, the angle between the two vectors is 0. If theta is 0, the sine of 0 is 0, which means the magnetic field is 0. This is telling me that a moving charge, a charge that moves in this direction, creates no magnetic field everywhere along this line. From here to anywhere here, the magnetic field is exactly 0. This is true only along this line. If you go here, you will find a non-zero magnetic field. If you go here, you will find a magnetic field. If you go here, you will find a magnetic field. Now here's the thing, the sine of theta becomes 0 also when theta is 180 degrees. So if you choose an observation location to be somewhere here, then the vector r will be this one, and from V to r you will have an angle of 180. So a moving charge, the charge that moves to the right, will create no magnetic field in this line as well. So everything combined, a moving charge will create no magnetic field along this line. Everywhere else you will have a non-zero magnetic field, but not here. Now, an extrapolation of this, something that we will use, if I give you, and actually this will happen in the lab, or maybe in a test. So if I give you a straight wire, okay, I know that I have some electrons moving here, and let's say my electrons are moving this way, and this is, as I said, I keep this wire completely straight, and then I bend it over here. Okay, so I have this, and whatever is going on there, I don't care. But this is a straight line. If I ask you, what is the magnetic field here from this straight wire? What's the magnetic field here? I do want you to remember that all of these moving electrons create no magnetic field on this line. And since my observation location, since I made it to be along this line, this current, the current that flows in this straight wire, will create no magnetic field here. But if you bring your compass anywhere else, say here, you will detect a magnetic field, but not on this point.